So our second presentation is going to be on demonstrating V93000 Wsmx HR analog performance requirements in TWS applications. And the presenters is Hersy Liu from Advantest. Hersy works at Advantest Taiwan, and she has ATE experiment in supporting MediaTek transceiver and NB-IoT Aurora TWS Bluetooth FT test program developed by the V93000 Smart Test 8. So Hersy, take it away.
Okay, thanks, Ying. My name is Hersy, and I'm from Advantest Taiwan. Okay, and my topic is demonstrating V93K Wsmx high-resolution analog performance requirement in TWS application. My presentation is divided into 4 parts. I will begin with TWS introduction, and then I'll move on to the instrument introduction. Next, we're talking about the performance comparison, and finally, we'll land on conclusion. The TWS full name is True Wireless Stereo. And from this chart, you can see that the TWS need to shore up the wearable market in these years. It is expected to grow about 30% in this year. Also, the wearable bands and TWS products have about totally 300 million units in 2019. And it is expected to become 760 million units by 2024. What we are familiar with the TWS is application, earbuds such as AirPods, Bluetooth connection. The earbuds connect with the smartphone by Bluetooth. It also allows all user behavior. You can use one earbud only, or you can switch earbuds. This is the device we used for the experiment in this presentation, the TWS device. It includes power management, USB, cap touch, audio, and many other functions. We'll focus on audio only. Okay, so let's talk about how does the TWS works. Relay is the most initial way in TWS. The smartphone delivers data packets to the main earbud, and the main earbud will separate right and left channel, then deliver another to the sub-earbud. To synchronize 2 earbuds, the sub-earbud will confirm with the main earbud after receiving data packet. So this causes the delay time between video from smartphone and audio from earbuds. Also, the main earbud needs to receive and deliver data packet to the sub-earbud. So the power consumption is much higher than the sub-earbud. This means the power consumption of 2 earbuds are unbalanced. So some different methods are provided to solve this problem. The master-slave rule is repealed in TWS+. The smartphone will deliver data packets of right and left channel to each earbud. 2 earbuds will do signaling, then decode and play the sound at the same time. This improves the connection stability, also let the power consumption of 2 earbuds the same. But this is only implemented on some specific smartphone. In Snoop method, there is still a main earbud, but it will not deliver data packet to the sub-earbud. After the sub-earbud will do the signaling first, then it can search for the data packet sent from the smartphone actively. MC Sync, multicast synchronization. It is similar as Snoop, Balanced power consumption, smartphone platform independent. You can use on both iOS system or Android system, but it have a more reliable connection, low jumpiness, low latency, and Snoop. So these are the 4 common methods in TWS. And the data package includes hundreds of signals. We'll focus on audio only. Moving on to the next topic. Here are the instruments we used: audio precision and the V93000 Wavescale MX card. This is the audio precision. Here are some ports for input and output signal. Using an USB transmission line, connect to a computer which have installed the audio precision software. Then you can observe the signals waveform, spectrum, SNR, THD, or anything you want to see without coding. One thing should be noticed is the audio precision's version and the software's version should be the same. And audio precision can be implemented on speakers, headphone, and microphone test. This is the tester we used, Advantest V93000. And the card for sourcing and capturing waveform is called Wavescale Mixed Signal High Resolution card. We usually call it Wavescale MX, like this picture. There are 32 instruments per card, and it equals to 16 units. Each unit have one high-resolution AWG for sourcing waveform and one high-resolution digitizer for capturing waveform. The resolution is 24 bits. All the instruments can be used in parallel, and there are 64 bidirectional analog pogos. Each pogo have a PMU for DC measuring. It also provides test processor controlled synchronization. All channels are independent and fully controlled by test processor. The memory is pooled. Large memory pool. There are 216 mega samples shared between 4 instruments. It also provides hardware signal processing unit for achieving better signal quality. Following is the V93000 data compared with the audio precision. There are 2 parts. Audio uplink, which use Wavescale MX high resolution AWG to source waveform into the device, and audio downlink, which use Wavescale MX high resolution digitizer to capture waveform from device. Bluetooth 5.0 audio uplink is ADC test. The AD source the waveform into the device, and then the waveform goes through the ADC converter in the device, then become digital code. We all know that the earbud can play the music, but have you ever seen that why we need to source waveform into the device? That's because a very common function in the TWS product, the noise canceling. Okay, so you can, and here the IC designer is interested in 3 kHz sine wave. So here we set the Wavescale MX high resolution AWG's target frequency as 3 kHz, cycle as 31, sample number as 2048, and the sample frequency is from coherence. You can imagine the audio precision is connected here to prove the AWG's performance. Okay, then we can get the data here. This is the time domain, and this is the frequency domain. The amplitude is around 175 millivolts. The power is around minus 15 dB, and the noise floor is around minus 135 dB. And you can see the harmonics are very low. So the IC designer is satisfied by the AWG's performance. Here shows the data in more detail. These are all the harmonics from audio precision. And you can see that this is the fundamental tone. It is at 3 kHz. The second harmonic, H2, is at 6 kHz. The third harmonic, H3, is at 9 kHz. When the fundamental power is normalized to 0, you can see that all the harmonics are lower than minus 110 dB. SNDR is minus 93, SNR is minus 93, THD is minus 113 dB from audio precision. So proved by the audio precision, the Wavescale MX high resolution AWG can source a high performance waveform. The audio uplink is ADC test. So after the device transfer waveform to digital code, then the tester can use digital capture to get the digital code and then combine them as waveform. This means the waveform goes through the device and then come back to the tester. Then finally, we can get the performance shown in this table. There are right and left channel, and the IC designer's requirement is shown as the low limit. We use absolute value in the data log, so maybe I'll skip the minus word in the following presentation. Okay, so the tester got the SNDR 91, SNR 91, THD 100 dB, and you can see that these are a little bit worse than the audio precision's data. And I think this is because of the distortion from device. Bluetooth 5.0 audio downlink is DAC test. The AT capture waveform from device. It is just like the earbud playing the music. And the IC designer is interested in 1.5 kHz sine wave. So here we set the Wavescale MX high resolution digitizer's target frequency as 1.5 kHz, cycle is 9, sample number as 1024, sample frequency is from coherence. We will compare different signal level. 0 dB large signal, minus 20 dB middle signal, and minus 60 dB small signal. If you don't have the feeling how large is the large signal or how small is the small signal, we can take the volume bar as example. We can say that the volume bar, the largest is 10 and 0 is mute. Then the large signal is 10 and the middle signal maybe is 6, the volume we usually set, and the small signal is 1. Okay, and same as the audio uplink, you can imagine the audio precision is connected here to prove the Wavescale MX high resolution digitizer have the high performance, which is correlate with audio precision. So we will compare the data of device to audio precision and device to Wavescale MX high resolution digitizer. Here shows the 0 dB large signals data. The black screenshot is from V93000, and the white screenshot is from audio precision. Time domain is at left, and the frequency domain is at right. So we can see the waveform first. The peak-to-peak voltage is 1.6 volts. It is just like the loudest in the volume bar. Okay, then we can see at the spectrum, the fundamental tone is at 1.5 kHz, and the noise floor is around minus 110 dB, and also the audio precision's noise floor is also around minus 110 dB, and both the harmonics are very low. So here shows the data in more detail. The fundamental tone is at 1.5 kHz, and the second harmonic H2 is at 3 kHz. The third harmonic H3 is at 4.5 kHz. And you can see that all the harmonics are less than minus 100 dB. The SNDR is minus 87, SNR is minus 87, THD is minus 95 dB from audio precision. And from the V93000 with Wsmx high resolution digitizer, the SNDR is 87, SNR is 88, are correct with the audio precision data and better than the IC designer's requirement, especially THD. Here's the data of the minus 20 dB middle signal. The peak-to-peak voltage is around 210 millivolts. It is 8 times smaller than the 0 dB large signal. And this is just like switching the volume bar to middle. Okay, and the fundamental tone is at 1.5 kHz. And we can look at the spectrum from audio precision first. The power is minus 20 dB, and the noise floor is around minus 120 dB. The harmonics are very low, and the tester will normalize the fundamental power to 0, like here, and then the noise floor become minus 100 dB, and the harmonics are also very low. So when the audio precision normalize the fundamental power to 0, then you can see that all the harmonics are lower than minus 90 dB. The SNDR is minus 73, SNR is minus 73, and THD is minus 91 dB from audio precision. And from the V93000 with Wsmx high resolution digitizer, the SNDR is 83, SNR is 86, and THD is 87 dB. These are more than 15 dB better than the IC designer's requirement. The last one is minus 60 dB small signal. The peak-to-peak voltage is around 2 millivolts. This is 800 times smaller than the 0 dB large signal and 100 times smaller than the minus 20 dB middle signal. This is just like you switch the volume bar to 1 only. And look at the spectrum from audio precision first. The power is around minus 60 dB, and the noise floor is around minus 120 dB. The harmonics are very low, and When the tester normalizes the fundamental power to 0, then the noise floor becomes minus 60 dB and the harmonics are also very low. When the audio precision normalizes the fundamental power to 0, you can see that almost all the harmonics are lower than minus 60 dB. The SNDR is minus 43, SNR is minus 43, THD is minus 51 dB observed by audio precision. And from V93000 with scale MX high resolution digitizer, the SNDR is 45, SNR is 47, THD is 49 dB. These are correlated with the audio precision data and more than 15 dB better than the IC designer's requirement. So this table shows both the audio uplink and downlink data. In audio uplink, which use the Wavescale MX high resolution AWG to source waveform into the device, we get the performance which are more than 20 dB better than the IC designer's requirement. And the noise floor is around 135. The in-band harmonics are all lower than 115 dB. In audio downlink, which use the Wavescale MX high resolution digitizer to capture waveform from device, this is the data of the 0 dB large signal. And we get the performance which are all better than the IC designer's requirement, especially THD. And the noise floor is around 110. In-band harmonics are all lower than 105 dB. My conclusion is that the V93000 with scale MX high resolution demonstrate high analog performance, especially for high quality and low noise TWS headphone products. And these are the reference websites. So thanks for your attention.
Thank you, Hersy. A reminder, if you have any question for Hersy, please put them into the Q&A box. And Hersy, first question will be that how many sites can the Wsmx test at the same time?
Okay, we can look at this slide. I've mentioned that there are 16 units per card, and each unit have one high resolution AWG and one high resolution digitizer. So this means that we can use 16 sites, the maximum. But it also depends on the implementation, such as if you use the IQ differential waveform, then maybe the maximum is the 8 sites.
Thank you. The next question is, did you need any special design on the DIP, the DIB board, to achieve these values, the SNR and the THD?
You mean the special design on the load board?
The load board, the DIB board, yeah.
Yeah, load board and DIB board are the same. Yes.
Okay. Yes, the signal output from device, and then it will go through some RC filter or snap filter, then go into the Wavescale MX digitizer. So you have to choose the RC value.
Okay, thank you. The next question is, how long is the test time for testing the audio uplink and the downlink?
The audio downlink takes about 30 milliseconds. And the audio uplink, because it will, the tester will source the waveform into the device, and then the device then capture the waveform from device again. So this takes a longer time. It is about 70 milliseconds.
And I have one last question here, which is in the middle signal, why the performance of the audio precision and the V93K are not correlated?
Okay. This is because of the calculated noise bandwidth. I didn't change the audio precision's noise bandwidth, so three of the large signal, middle signal, and the small signals calculated noise bandwidths are the same. But in the tester, the large signal and the small signals noise bandwidths are wider than the middle signal. So this is why the middle signal's data is better. Okay.
All right, that's all the questions that we have, Hersy. Thank you again for presenting great presentations.
And lastly, I would like to thank our sponsors who made this event possible, including free registration. Our premier sponsor is Kohu. Our emeritus sponsor is JonsTech. Our honored sponsors are ISC, iWin, and TSE. Our distinguished sponsors are Backer Hotwatt, Innovative Circuits Engineering, JMT, Nidec SVTCL, R&D Altanova, UI Green. Our exhibitor sponsors are ELELS, MJC, Phoenix Test Arrays, and Smith's Interconnect. So please, when you talk to them, thank them very much for making TestConX 2021 possible. And an extra special thank you to our premier sponsor, Kohu, the market leader in test interface solutions for the most challenging applications. And thank you to ISC, the global #1 total test solution provider. With that, I will thank you all for attending and wish you a very good rest of your day, and look forward to seeing you again tomorrow at 7 a.m. Pacific time. So thank you.